Hello, my name is John Morris, and I will be discussing my research into designing a procedurally generated Metroidvania-style video game using answer set programming. Um, this research is also in conjunction with a game that I am creating with a student of mine. I am a programming and game design teacher, and the game we are making is called Last Winter. As far as that game is concerned, it's still in process and has a long way to go, but as far as the generating of maps, this is what my research is into. All right, so as I said, my name is John Morris. My advisor is Dr. Somerville. And then the student that I'm working with is named John Yu, and he has created all the art and basically has done the game design, the character controller, and most of the stuff. I'm basically focusing on generating the maps, as you can see here. So on the right, you see an actual map. This is the current state. You can see, so the white area is open area, and this kind of bluish is the tiles that my student created. And there are some lava and water, and it's kind of hard to see in this picture, but there's some doors and things like that. And then over here on the left is an example of how the first step into creating the actual map on the right. So we have a graph that then dictates the map on the right. And I'll go through all of this. So Metroidvania. What is Metroidvania? I imagine many of you do not know what it is. It is a subgenre of action-adventure video game defined by two classic video games, Metroid and Castlevania. Specifically, Super Metroid, which came out in 1997 for the Super Nintendo, and Castlevania Symphony of the Night in 1997 for the PlayStation. All right, so this is a video of Hollow Knight, which is a much more modern Metroidvania style game. This happens to be my favorite Metroidvania game. This is the trailer for the game, showing some of the gameplay for those of you who don't know what it is. As you can see, it's a 2D platformer. There's a lot of elements, as I will discuss, about exploration and opening up new areas with abilities. Like here's this guy, I forget what that ability was called, but he can shoot across the room. Special sword abilities and all different kinds of things. There's an item system. So most of these things I will not be discussing because they're not relevant to my research, but they are things that are being developed in the game that I'm working on. All right. It's not letting me go. There you go. All right. So common characteristics of Metroidvania games, they tend to be 2D side-scrolling platformers. They're not all 2D side-scrolling platformers, but they tend to be. They heavily focus on exploration. It's about discovering. You discover items and abilities while exploring, and then with those abilities and items, you unlock areas. So then there's a lock and key. I'll often refer to them as like lock and key puzzles. So you have an area that is locked off to you. You have to find some sort of key somewhere in the available areas that then allow you to open up new areas. And then because of that, a major component is backtracking. So one of the very common things, especially in the game on the right, Super Metroid, is you will come across an area that you can see that you want to get to, and you try to get to it. Maybe maybe you need a high jump, or maybe you need some sort of special ability, but you can't get to it. And so then you have to go somewhere else in the map to find the item that will, the key that will open up that area. And so these are actually more or less color-coded. It's not entirely correct. There's, within each color group, there's locked off areas, but in general, it's color-coded, showing the areas that are initially locked off, and then it slowly builds. The world slowly gets bigger, or the places you can visit get bigger. You start up here where the little ship is, and then you can access, and I believe, it's been a while since I played the game, but I believe you go down one of these shafts, and you get down here, and then you have to find the items that you need, and then you go back up, and you unlock other areas. And that is the nature of Metroidvania games, about exploration and unlocking ideas, areas. Here's just two more layouts. On the left is the Hollow Knight map. It's just it's more of an artistic interpretation of the map, but this is essentially the layout of the game, and you can kind of see the color coding. Like, so this is the main area you start in. It's pretty big, and then everything slowly opens up as you get items and you unlock things. And on the right is the Symphony of the Night. Same basic idea as before. All right, so now let's talk about answer set programming. So answer set programming, I'll usually refer to it as ASP, is a declarative programming paradigm which finds stable models, referred to as answer sets, that satisfy a series of user-defined constraints. So you're going to be defining the domain that you are wanting to find a solution for, that you're wanting to find a set of things for, and then it will come up with a set of things that will satisfy the answer set. It will come up with a set of things. And in this particular case, they're called predicates, and I'll show you what those are. So answer set programming is usually defined in ANSI Prolog, which is a logic programming language that extends Prolog. And then, so answer set programming can be used to define the conditions and rules necessary for successful completion or navigation of a Metroidvania style game, as well as other style games. And then it'll randomly place different types of geometry, so different things in the world that are obstacles, such that the rules and conditions are met, and therefore ensuring a winnable procedurally generated game. So we're talking about procedurally generated. Procedurally generated games are games that you are generating the world when you play it, or at least it's been programmatically created versus an artist sits there and actually makes it by hand. And so normally when you do a procedurally generated game, you then have to check. You have to have some sort of algorithm that will then check to make sure it is winnable. But using answer set programming, all of that gets done for you in the initial build, or in the creation of the world. All right, here is a very common example of answer set programming, the n-queens problem. The n-queen problem is a problem where you have an n number of queens on a n by n board. Could be a chessboard with 8 by 8, or it could be any size board. And the rules are that you have to place all the queens on the board such that no queen is in immediate danger, meaning there's no queen in another queen's line of attack, and then that would be vice versa, because that's how queens work, right? Because for those of you who aren't familiar with chess, the queen can move in basically every direction, diagonally, horizontally, or vertically, until it hits something. So a typical way that you would solve this problem, not using ASP, would be a backtracking. And one way to do this is you could say you're going to start, so you're going to go column by column, and you first put a queen in the first row, and then you go to the next column, and then you go down the rows until you find a safe place to put a queen, and then you go to the next one. You keep doing that until you can no longer place a safe queen, and then you have to go back to the previous row, move the queen down, and then keep doing that until you finally find a set. ASP, in order to do ASP, it's actually pretty straightforward. All you have to do, instead of creating some backtracking algorithm that's, somewhat complicated, all you have to do is essentially define how a queen moves, right? So in this case, we're talking about a queen, but in the case of like in a video game, you define how can the player move and what are the constraints. So here I'm going to show you an example of code. So all it takes is the queen's movements, how the queen can move, and the dimensions of the board. All right, so the first two lines, these are, like I said earlier, so these are called predicates. So there's a width predicate and a height predicate. And when you see this 1 ... or any number on the left and then another number on the right, it will create a predicate, so it'll say width 1, and then there'll be another one called width 2, and so forth, all the way up to n. And those are what are used, and this is actually referred to as you're declaring, you're stating facts about your system. So there's all these things called width and all these things called height, with a value inside, one parameter. Here on this line we have queen x, y, x, x, y, y, and so we have a predicate called queen with two parameters, a x and a y, and then there is these curly braces, and this is the principal thing that is different than ANSI prolog, is my understanding, that the curly braces are giving the solver a choice. Yeah, it's a choice rule. So it can create a queen. It can place a queen at this position, and then here is called the neck, and the position is at some combination of x with some value, and then a width with some value and height with some value. So you're going to get an x and a y at some position, right? So we have our 1 through n in the width, 1 through n in the height, and so it's going to randomly place 1. All right, so the next line, what it's actually doing is so we have the neck. Yeah, I didn't mention that. So this is called the neck. It's a colon dash. And what it's saying is this cannot exist. Whatever's to the right of the neck with no parameter on the left is saying that the thing on the right cannot exist. And what this is actually saying, so here's the curly braces again, but in this case what that's doing is it's a count. So how many queens are there, how many predicates are there with the name queen? And the underscore is saying, well, I don't care what the value is. So any queen of any value. And I'm saying it cannot equal n. But like I said, this is a restriction. And so what that means is it cannot be anything but equal to n. So that's how I get n queens on my n by n board. The next two lines deal with the horizontal motion. So in this case, what we have is we have a queen with an x and a queen with another x. So they have the same x value. So they have the same x value, and then the y does not equal themselves. So what that's actually saying is, because I'm saying that they can't be the same. It's a weird little thing you have to do. It's saying that it's not the same queen, but they can't have the same x value with different y values. So it's saying you can't have them on a horizontal, and this deals with the vertical, same idea. And here are the diagonals. In this case, the diagonals. This is a little trick. Since my width contains all the values from 1 to n, I'm getting a value of a number 1 through n, and I'm adding it. So this would be the up 1, right 1, up 2, right 2. So it's always going to be the same. So it's going to just check, is there anything up s and right s and up s. And the next line's for the down. The down. So it's going to be, right s, down s, so on and so forth. And here is a demo that I have, and I'll put a link in the video, but I have a little demo set up on Google Colab that you can play with and actually run this code. But I will not be demoing that. All right, so ASP for Metroidvania. So why? Why would we want to use Metroidvania? I've kind of already explained it. Why would we want to use ASP for Metroidvania? Like I said, the lock and key is a major component. And if you're procedurally generating things, you're placing keys and you're placing gates someplace in your world. You need to make sure that every key is accessible. It's not locked behind its own gate, or there's not a series of gates such that there's a key you can't ever get to because of the other keys that you need. So that's a major thing. All of the research that I've seen for this particular approach tends to be it's some sort of brute force method where you just randomly place things and you just check to see if the key is accessible, and if it's not, then you redo it. Where ASP will only return a solution that's correct. And the next line is control pacing. Now this is something that I'm not doing for my research, but it is something that I will be implementing with the actual game that I'm creating with this research. And so what that is, you're going to actually control, say, like how often are you running into enemies, the frequency. So like how often do you run into an enemy? How often do you get a relaxing point? So this is one of the big deals in game design, is the pacing. And now we have the generating of the terrain based on the player's movement ability. So like I said, it's kind of like the Queen's example, but the terrain is set, right? It's just a board. There's no walls or anything. But here I'm going to put in walls. And it's going to be dependent upon, here's just some examples. We have a jump, so how high can the player jump? The speed, and how the speed affects is, well, how fast can they move? So when you jump up in the air, how far can you move to the right or left while you're in the air? Wall jumping is a common thing in video games, as well as Metroidvania games. Double jumping, same thing. But neither one of these, I have not implemented these in my current iteration, but these will be future tasks. But I do have, as far as my gates, so we have doors and obstacles. So doors is just like a regular kind of door that you have to have a key to open. And obstacles are, like in that first image I showed you, we've got water hazards and lava hazards. So something that's going to restrict your ability without, your motion without having the correct ability. And the last thing, which I think is honestly maybe one of the most interesting, is aesthetic features that ASP can do. So in the particular game I'm working on, we're going to be placing lighting using ASP. And we're just going to define the rules. We want to make sure that there's light in the right place, but we also want there to be darkness. This is kind of actually going to be very similar to like the pacing, controlling of pacing, where you want there to be dark areas, but you want there to be better lit areas. And ASP can actually do that fairly easily, and then also adjust the terrain, right? So if we do it all at the same time, you can get lighting and everything placed in the right place in the terrain such that everything works out. And then you have the background and foreground. So this would just be, these are all aesthetic features. So the non-interactable things, and then actual non-interactable, meaning like things in the plane with the player, like grass and other types of just objects that are there for aesthetic purposes. All right, so here is really kind of the only research into ASP for Metroidvania-ish things. This actually is specifically more for a Zelda type game. Many of you may be familiar with the diagram on the right. That is from the Game Maker's Toolkit Boss Keys series, where they talk about this exact whole idea of having a lock and key map. What Smith did in his research is he actually created this map in the middle here, and more specifically, the paper, anyways, is about the notation and the approach, how to develop the map and make sure that the keys are in the right place and not behind gates, and the notation. Like here, these T's are actually branches. They're traversal nodes, and then you have you have keys and locks and so on and so forth. And then this map on the right is actually the abstraction of this map showing the hierarchy. So in the boss keys notation, you have diamonds, and diamonds are keys, squares are gates, and this is actually the same notation that I use in my maps that you will see, my graphs that you will see. And also, it shows it hierarchically. So what it's showing is that this key, which is the bow and arrow, is a little bit higher than this gate. So it's representing that you have to get this, even though they're color coded, they're actually semi-color coded. This is kind of blurred out, but it's supposed to be the same color. And you have to get the bow and arrow in order to get through this gate, and then you get this key, which is just like the map. And then, but then you have to come over here. You have to get this red key in order to get the red gate, and then you also need to get the the boss key in order to get through. So that's why everything is showing the order in which you have to do things in order to get to the boss. All right, so interactive conflict resolution algorithm. So this is a term that I'm referring to what I had to develop in order to actually create these large expansive maps using ASP. As one of the problems with ASP is the larger the problem, the increasing in runtime. And for my specific case, I'll show you the data. It just becomes way too long. It takes way too long to solve. But before I get that, I just want to explain the concept. So on the right here is showing that the maps are actually generated of tiles made up of discrete elements. And so this area here, this sort of more navy blue, is actually empty space. And then these parts are the collision tiles, the non-empty space, or what I actually refer to as filled in my ASP code. So these are filled, and then this is empty. And so you do that for the purpose of ASP. We do this because this makes it much simpler to generate a map. Just like the that's going to be very similar to the n-queens problem, where you have a grid system set up, and then you're just basically playing tiles. You're placing tiles. And for every single coordinate, you're either putting a tile or not putting a tile. It's either filled or it's empty. All right, so here is the data that I was talking about for the runtimes. And on the bottom, you have the n by n. So these are all just square rooms, and it's a number of tiles. So as it increases in size, the runtime exponentially just goes out of control. Here we had a 70 by 7 or 75 by 75, and the numbers actually, this may look a little strange, but one of the things about ASP is I actually had a run, I think it was a 70, that took under 2,000 seconds, but the average of all the runs was around 6,000 seconds. So because there's a lot of randomness involved in finding a solution, you don't have concrete runtimes. It's very variable, but you do have an average, and the average is this exponential curve. So I had to figure out a way to break it up. Well, that developed the next problem. The next problem is, and what this animation is showing, this is actually an actual map being built. And what happens is you build one map, actually starts in the upper left corner, and as you can see, it went from left to right. And then you see them disappearing every time. And the reason why it disappears is because the next room next to it ran into a conflict where it couldn't build because of the geometry of the surrounding rooms. And so what the code does is it finds a neighbor that's affecting it, so it has openings to it, and it will randomly delete it if it runs into an unsolvable situation where it can't come up with a solution. It also might do it if it runs out of time. I put a time limit on it because that's one of the other issues with ASP is there's no upper limit to how long it could take with the particular seed, because you pass in a seed, and it could end up taking forever to find a solution. So I put in a timer to exit and then try again. And in this case, one of the things that could be causing it to take too long is conflict with the neighbor. So it also deletes a neighbor if it runs out of time. All right, so now let's talk about the world maps, the world graphs. So a world graph is defined, it's in a grid, placed in a grid, width by height. In this case, we have an 8 by 8. Most of my maps were square, but they didn't have to be square. I just tended to do them in square fashion. And then for each room, right, so the numbers, the nodes in this graph are all rooms, and then the arrows are doors, connections. And obviously each room could have up to 4. And here's the only one in this map that has 4. It actually, I put a lot of restrictions into it because of runtime concerns that if it has too many connections, especially if it's a directional connection, like here's a directional connection. I don't allow any if a room has a directional connection, it can only have 2 doors. So one entering and exiting. So it's one bidirectional door and then one directional door. And it just helped with the runtime to solve the actual rooms. And yeah, so they're either bidirectional, directional, or not connected, no connection. And then every room has a path. There exists a path from any room to any other room. And that's just to make sure you don't get stuck. All right, so this is the ASP code. This is, I definitely am not going to be able to show all the ASP code because it's just a massive amount of code. But here is just sort of the initial setup for this map. So like I said, so here's some constants. This is how you define a constant. And this is actually passed in. So this is defined in the code. So if I don't pass in a max width or a max height, these are the default values. And you pass it in through the command line when you call the solver. And so this is the, so in this case it was 8 and 8. And then this next line, it sets up the grid. And so I have a room grid, X and Y, and an ID. So it's a X coordinate, Y coordinate, and then a room ID. And the room ID is, so right here, this is actually a calculation. This calculates what the room ID would be based on this random X and Y coordinate. And so this is actually done a little bit different than I did with the Queen's problem. Here I'm saying, because I'm saying 1 and 1. So what that's saying is that there's, at minimum, there has to be 1 for this combination of things, and a maximum 1. So it puts 1 grid at every X and Y, every combination of X and Y. And then this just calculates what the ID would be, and it places it right here. And then here, now what we're doing is now we're saying, well, how many room IDs are there? Because this is how all the rooms are identified, is by room ID. And so there's 1 to the width times the height, which should be kind of obvious. And then now we're actually placing the rooms at each ID. So I'm defining and I'm assigning it to a grid room. And then this is the last time I used room ID. Basically, room grid was just used to set up the doors and set up the doors right here. So now setting up the doors. So a door starts here and goes there. So I have from room ID 1, I have a door that goes to room ID 2. And here's that same thing. So I have 0. So there's an implied 0 here when there's no number. So I could have 0 of this door from room ID 1 to room ID 2, but up to 1, right? I don't want there to be more than 1. And then it gets it from a neighbor, right? So here is the XY, room ID 1, and then plus 1. So it's the room to the right. So there might be a door there. Here's the room to the left. Here's the room down. So it's a little bit confusing. My Y coordinate increases as you go down. And then this is up. Negative is up. So the first row is 1. Second row is 2. So on and so forth. And then we have a start room. There's exactly 1. So there's a 1 and a 1 on the outside of the curly braces. And then we have the, it randomly picks one where Y is equal to 1. Because I want it to be at the top. We want the entrance to be at the top. All right, so yeah, so start room is random, but always in the top row. And then keys and gates are color-coded, red, blue, yellow, as you can see here. Key rooms are diamonds, just like the boss key diagram. And then the gate rooms are squares, same thing. And the gates are between 2 rooms. So this is where things start to diverge, because in the boss keys, it doesn't show the boss key diagram. It doesn't actually know anything about directionality. It's just showing connections, how things are connected. But I actually have directional paths, so things are much more need more refinement. And so a gate is in one room and it gates off another room. So that's why you see the arrow, the colored arrow, is showing which room does it gate off. And then there's also a boss room. They're here in gray. and the boss room has a gate. So that's one of the constraints. All right. Yeah, so there's a path between any two rooms, and directional paths are only used to enter or exit a gated area. This was actually done because of an error that was found in the initial, the initial setup of the map of the graph system, was that you could, and then also this was an interesting fix because it made the world much more interesting. Because so in this case, it's a directional path into a, in this case, it's going right into where the key is, but this whole area is gated. So see, these gates are gating off, but technically, in this case, since it's a key gated area, they're actually they're preventing you from exiting. So it's not gating you from this area. What it's doing is it's locking you into this area to ensure that you get the key. And so that made sure that you didn't end up, because what was happening before with these one-way passages is it was assuming, the code was assuming that you had the key because you could get to that point, but if you didn't pick it up, you could get stuck. And so I made it so that every directional door either goes into a gated area or goes out of a gated area. And in this case, there's not an example of exiting. And here is the code for, or one little part of the code for the keys. Right. So we have a max gate type count. And there's actually also a min gate type count, but it's not defined here. So those variables are passed in. And so you don't actually, if you pass in a variable, you don't actually have to have it declared like this, which is kind of interesting. So we have key types. So there's going to be a number of keys. So in this example, and in this example, there was 3. So there's going to be 3 different types of keys. And there's this key present with a 0. So there is no key, there is no 0 key, but ASP, because I'm going to use this, so ASP will throw an error if you don't have it. So I'm looking for this predicate, looking for that predicate, but if it doesn't exist, ASP will say this does not exist, and then it'll just break. And what that is for is if you're entering a world, so if we're going to generate a world where you already have the key and thus don't need to pick it up, we have that. So if you're, like, let's say you were going to have key type 1, then you would say key underscore present with a 1, and then it wouldn't actually put in that key. All right, so here's the placement of the keys. It's just going to randomly pick, right? So I want 1 key for every key type, and then if not present. So if this key present of that key type doesn't exist, then I want you to place 1. And so this is the key ID, and then this is the room. So what room is going to be in? And then this is just the list of all rooms. So it's just randomly going to pick some room to stick it in. And now here are the gates. So the gates have a minimum number of gates, and they have a maximum number of gates. For this example, I think it was a minimum of 2 and a maximum of 100. Obviously, there's not anywhere close to 100, but I was just wanting to make sure there was no upper bound preventing it from placing gates. And this is very similar to the key, to the key one. And now what we're going to do is, and then there was just some additional restrictions here. But here's the interesting part. So now we want to make sure that the key, you can reach each key. So what we have is this predicate called have key, the key ID, and then the time step. And so the time step is saying, well, where are you getting this key from? At what time? How far away are you from start? So as you can see here, so path order, and this is all out of order. Path order is at the start room, starting with 0. And then let's go to the next derived path order. So you've got the room ID. It has to have a door to, so it's a door from a source room into this room, and it has to have a path order. And then it has, and then the t value. So then you add 1 to the t if it's not a gate. And this is just a limiting factor that you need to use. And then if it is gated, like in this case, so this is the same thing all the way up to here. So instead of not gate, there is a gate, you need to have a key. And the key, so there needs to be a key for that type, right? So there's the key ID, and the key, so it's called T2, the current T, so the current time step for this gate has to be greater or equal to T2. And so that actually makes sure that the key cannot be placed at a time step behind its gate. All right, now there's rooms. Here's the animation again. So rooms are generated one at a time. And the entrances and exits, the path through the room, are generated programmatically, depending on the neighbors. So basically, I take the code, like actual strings of ASP code, and pass it into the solver. Actually, it creates a file. All the text gets saved to a file, and that gets passed into the solver. You also need to add in the neighboring room's geometry, right? So that the doors match up, as well as the starting points for the paths, and I'll talk about what the paths are in a little bit. Because you need to make sure that the paths start. And the principal issue with those path nodes are with the vertical paths, the up and the down. So all the code, basically all of the rooms are broken up into these 5 components. So you've got tile rules. Tile rules just simply are based off of the art. What available art do you have? Where can you actually place a filled tile such that you have a piece of art that will fit there? And then you have the player movement rule, so that's just how can the player actually move and walk around. And then you have the platform rules, and the platform rules are actually just something that I use to kind of simplify the code. It breaks up each room into, at most, 5 platforms. And then you build paths between those platforms. So that's the path rules. And the gate rules are just what type of gates are there? Is it a door? Is it a water hazard? Is it a lava hazard? And then you have to actually place those tiles. All right, so here is the tile rules. So like I said, you just have a certain list. In this particular case, we only had 13 different collision tiles, and this doesn't have them all. It has almost all of them, but so it's showing the arrangements. How can you have them organized such that you have art for every type of placement? So this actually is the defining factor in the shape of what your map's going to look like. In this case, there's no diagonal tiles, so there's not going to be any like ramps or anything. And now we have the player movement. In this case, so the player can jump up 3 tiles. The player can move left or right as on a platform, and then the player can also fall. Now this isn't entirely accurate because gravity doesn't allow you to go. So what the rule is, it's every tile down you can go left one or right one. That's not actually how gravity works, but because of the scale of each room, it actually works pretty good. And then we also have because the player is 2 tiles tall, for every path. So everything that's going to be declared as a path, there has to be at least 2 tiles above it. And so here you can actually see that. So this is a path node. So this tile is on the path, and then because he's able to jump up, there's actually a path point here. So that's why there's 3 here. And here is some of the little code. So here is so initially, actually this is used a lot. So what is a floor? Floor is defined as a tile that's filled, right? So like this guy. And then the tile directly above it is empty. So all these ones that have empty tiles above them are defined as floor. And then here is the jump headroom offset. So that's what I was talking about with the two tiles above the head. And then so here is a predicate that's defined has headroom, and it just makes sure that it actually has headroom, and then you use that down below. Now these 3 are required because the player can jump up 3 tiles, which then means the player can jump up, and because of the rule of falling, but it also goes up, for every tile up, you can go over 1 tile. And so I actually have to have these 3 sets in order to take care of that. Now, if you wanted to, if this was fixed, so this is fixed at only three tiles, but if you wanted to actually be able to just change it, like in your game, whatever game engine you're using, you want to change the player's height ability, you could have it programmatically generate these. Because as you see, so this is for up 1 and right or left 1. This is for up 2, right 2, or left 2, and this is for 3. So it's getting bigger and bigger and bigger as it goes, because it's got to check every single one of those tiles in between. Here's the platforms. There's up to 5 platforms. Here we're just showing 3. So we have the right platform and the left platform and the middle platform. And the way this is all set up in the pathfinding rules is you have to get from, like, this is the right platform, you have to get to the middle platform, and in this case there's a directional path. You can only go left. And you can see that there's no, so right here there's 4 blocks. You can't actually get up to here. So you can enter from the left, but you can't go out to the right. And then platforms, and the way platforms are defined is with those rules, right? So because there's 4 here, so you could have potentially gotten up to here, to the middle one, and then go over to the right, but you can't actually get there, and the color coding is actually kind of showing that. So if the player could get up there, these would all be green, but they can't. So these ones are all yellow because the left path system can't get to the right. And this is just showing that same idea. So the player can get from here to here. Player can't get from here to here. Can't get up there. So this is a left to down direction. And now we have a gate. In this case, this is the door. And what it does is just restricts the path. Right. So from the middle, this is all the middle, even though it looks like it's kind of on the side, but that's actually the middle platform. And it's preventing the bottom platform, it's preventing actually the up platform, which starts here, from getting through to the bottom platform with this door here. And then here's an example of a lava gate. And in the case of lava for the actual game, you just have to be submerged. So you have to, if the path goes through lava at all, you die. For water, it's a little bit different. You actually, in this case, we're doing 6 tiles, but this is much more than 6 tiles. But that's how the ASP works. I just set the minimum that you have to, in order to make it a proper gate, then it has to be at least 6 tiles, and then it's a proper gate. And then here, this is actually also representing a current bug that's in the room system, the room ASP code, in which the player could actually go around the water. And so this is something that needs to get fixed. And here are the current results for run times of the maps. And like I said, so as far as my research is concerned, this is what it's all about. It's just generating these maps. Has nothing to do with the actual creation of the game. So for rooms with no gates, it's about 45 seconds, and so it could be 5 seconds, it could be a minute or something like that. It could be 50 minutes, but the average, in fact, actually, when I do the gates, I found the number to be pretty good at 45. So actually, I put the non-gated rooms, I put the timeout time at 45 seconds, and so it works pretty good. The door-gated rooms, it's around 500 seconds. So those aren't that bad, but then the water and the lava gate rooms, 1,200 seconds, and sometimes it takes much longer than that, but that's about the average. And now the maps. So the map system, creating the actual graph. So I can't make anything smaller than 5 by 5. It will be unsolvable. For 1 gate, it takes about 5 seconds. For 2 gates, it's unsolvable. For 6 by 6, 1 gate's around 50 seconds, 2 gates around 200 seconds, 3 gates, unsolvable again. You see a similar pattern with the 7 by 7. You can get all the way up to 3 gates is also unsolvable, but then the 8 by 8, it's solvable, 1,200 seconds. And that doesn't always happen. sometimes it just gets stuck and never solved. So this is actually a major point for the actual rollout of the game that I need to work on and fix. And this concludes my presentation. Thank you.